compound being positive, 95%. He needs that kind of a compound.
No security guards.
No security guards, sir. And for 5 months they cannot figure out. They send doctors into in the guise of getting some vaccination, etc. And so So if we use the same thing, 95% and 5%, I get 95%. That's what Maya was saying. The whole thing was about whether the compound can be positive depending if Bin Laden is there or not. So that was where the whole discussion probably was going on. So if the compound will be positive, if Bin Laden is not in compound, the probability of compound being positive is very low. That's what the whole idea was. Okay. Fine. So Bayes' theorem, clear. Reverse probabilities. Okay. Now let's understand a little bit more about confusion matrix and other things. So credit card fraud increasing year by year. 1993, 2014 is already 16 billion. By now would have crossed $20 billion a year. So it's a major problem. E-commerce companies also face significant amount of that. So let's say there's an e-commerce site that has been offered a new system that can detect fraud. Okay? And let's say it has an accuracy of 99% in correctly identifying fraud. And 1% of the time it says honest transactions are also fraudulent. Happens. Sometimes you make a transaction and suddenly it's blocked, you get a call, did you make it or not? Kind of things. Happens. It happened to me quite a bit, both here and in the US. So, some real stuff there. So now, tell me, from a business angle, what will be the implication of the retailer mistaking an honest transaction to be a fraudulent one? So the transaction is good, but your system, that system that is given to you, it says no, it's a fraud. You will lose the customer. You are a strict person. One time someone does that and you kick them out. Well, then, yeah, there is an implication that you might lose. You normally don't lose in one or two times, but if you repeatedly do that, okay, if repeatedly it's doing that, I'll say useless, let's get out. You will lose the customer. What will be the implication to the retailer of mistaking fraudulent transaction as honest? Loss. No? So someone is committing fraud, I have not bought it. I will eventually not be paying. The retailer is losing some business. Someone has to pay. Okay. So honest. So there is a fraudulent transaction and it says honest. They don't catch it. So they lose business. Now, which one is false positive? Which one is false negative? Or first one is false. False negative, false positive. How many false negatives? How many false positives? How many? How does it matter? I don't have an e-commerce company. Okay. false positives. Okay. Yeah, what is positive here? Fraud. Detecting the fraud. Fraud is positive. So when I say that this transaction is fraud, I am saying it's positive. But it's really an honest transaction. So false positive. The first one is false positive. Second one, I am saying that it is not fraud. It is honest. So I am saying negative. It's not fraud. But I am wrong. False negative. Okay. And the more critical one, second one, unless this happens a lot, second one is more critical, especially if this is an expensive product also. Okay. False positive. False negative. Okay. Okay, in this problem, which conditional property has been given to us? Which conditional probability or probabilities have been given to us? There are only two numbers, so I need to. What is 99%? Yeah, in terms of conditional probabilities, tell me. Correct. True positive. So probability of detecting it as fraud, given it is fraud. Probability of marking it as fraud, given it is fraud, is 99%. In conditional probability, you have to give that given as a given word has to come in. Anytime anybody asks you conditional probability, the word given has to be there. The line there, the pipe, that is the given word. Okay. So probability of identifying fraud or marking it as fraud or detecting it as fraud, given it is actually fraud, is 99%. So now what is this? Probability of? Yeah, marking it as fraud, given it is not fraud. Because it's an honest transaction, given it is not fraud. So that's one question. Okay. Okay. So probability of, or flagging it as fraud, given it is fraud, 99%. Probability of flagging it as fraud, given it is not fraud or honest, 0.1. Okay. What other conditional probabilities might be useful or can be obtained here? Which cannot be directly read from here. Not flagged fraud, given it is fraud, this is only 1 minus of that. So that you can calculate from there. Okay. So those are the things I am asking. Those of you who are not able to get what I am really asking. Okay. So one of the possible conditional probabilities, probability of not flagging fraud, given it is fraud. But then I can get that from here, 1 minus of that. Okay. Any other things that I cannot get directly from here. Likewise, I can say probability of honest, given honest, 1 minus of this. That also I can get from here. What other things I cannot get? Probability of honest, given, which is this probability of it honest, given it is flag fraud. Okay, so that is the reverse probability. Good. Yeah. And the other one also, probability of fraud given it is flag fraud. The reverse probabilities. Okay, good. So now let me ask you a couple of questions. Suppose 1% of all the transactions are fraud in this e-commerce company. They have already noticed that. Historically, they have seen 1% of all transactions are fraudulent. what are the chances that the transaction is honest given the system has incorrectly flagged it as fraudulent? You just have to think that statement for a little bit. What am I asking for? Probability of what? Probability honest given given flag fraud. So that's the incorrect one. It is incorrectly flagged as fraudulent. It means it is honest. I am just repeating myself actually. So actually it is honest. And that's what I am asking here. I need not even have said that here. Incorrectly word. Redundant actually. What is the probability that the transaction is honest given the system has flagged it as fraudulent? Is that what I am asking? Okay. Given it has flagged fraud. Probability of fraud given to me. Now tell me Bayes' theorem. What will be? How will I get this property? Probability of in the numerator, first term in the numerator, what is it? Probability of honest. Okay. The second term in the numerator? Probability of flagged fraud given it is honest. Denominator? Probability of flagged fraud. Now flagged fraud, it can happen two ways. When it is really fraud and when it is not fraud. Okay. True positive, false positive. Okay. Probability of flagging fraud. Flagging as fraud is the positive. So it can have a true positive and a false positive also. So those are the two branches. And so, probability of honest, how do I get that? 1 minus of 0.1. Probability of fraud is 0.01. So probability of honest 1 minus 0.01. 0.99. Probability of flagging fraud given it is honest. In the first thing, 99% plus 1% we had given that. The problem had given that. Okay, so that part is there. The bottom first half is the same as that non numerator. Then probability of fraud. So probability of flagging fraud when it indeed is fraud. Okay? And that I get probability of fraud, I know. Probability of flagging fraud given it is fraud. We know that? Flagging fraud given it is fraud. So those numbers are given to us. I just plug them back in here. Okay? 50%. You see, again, the Bayes theorem. 99% of the time it correctly catches the fraud. 1% of the time it says honest transactions are fraud, it says. But yet, when it flags something as fraud, the probability that it is honest is only 50%. And you see why. That is because this term is also pretty large. The probability of fraud itself is pretty low, or probability honest transactions are a lot. Probability of fraud is pretty low. And then flagging fraud, this number is very high. Flagging fraud when it is fraud is very high. It correctly catches that. So this term here also becomes very large. This part is the same as numerator. This part also is a pretty large number. So that makes it low. Now let me change the problem a little bit. Instead of 1% fraud, if the e-commerce site has 5% fraud, then what happens? We use the same thing. Now the numbers have changed slightly. 16% is the answer. You see, now when it flags fraud, the probability that it is honest is 16% only. 84% of the time it's fraud. Okay. So it all depends on that number there. Okay. Makes it a small number. now what, you will put the business hat and now you will tell me the evaluation for the system. You were asked to evaluate the system for your company. Is it an adequate system that captures fraud 99% of the time correctly and 1% of the honest transactions only it says are fraud? If I had given you this problem early on, you will say, well, yeah, let's take it, 99% of the fraud is capturing and all that is fine. Now, given all your base theorem analysis, now what would you do? Will you recommend this to your company or will you not recommend this to your company? Why? So in that case, so you will not recommend, in the first case, if the instance of fraud in your company is very less, then even with that kind of power, it is not good enough to capture it correctly. So, but if the incidence of fraud is much more, then this accuracy is pretty good to capture. So 16%. 16% of course you will, depending on if 16% is acceptable enough or not. So that's the way you have to make a decision. You can't just go by 99% it can capture the fraud correctly, 1% only it makes a mistake. That's how we would understand if you don't know base theorem. Now we know better. Okay? It depends on the incidence of fraud itself. Great. Buyer or non-buyer, marketing campaign. Now you are in another company or in the same company, the marketing team is asking you, they are using analytics and then you are providing a prediction that these people are going to buy, these people are not going to buy. So that you don't waste your marketing expense and you actually market it to the people who are likely to buy. You are not going to be marketing, sending marketing material and wasting money to people who are not likely to buy. And let's say your company is selling some very expensive products. Now, which one is more important, which one is less important? If this is what your confusion matrix is. Okay, let me ask you step by step the questions. What is true positive yield? Marketing expense and you actually, it depends on much more. Then this accuracy is pretty good to capture. So 16%. 16% of course you will, depending on if 16% is acceptable enough or not. So that's the way you have to make a decision. You can't just go by 99% it can capture the fraud correctly, 1% only it makes a mistake. That's how we would understand if you don't know base theorem. Now we know better. Okay? It depends on the incidence of fraud itself. Great. Buyer or non-buyer, marketing campaign. Now you are in another company or in the same company, the marketing team is asking you, they are using analytics and then you are providing a prediction that these people are going to buy, these people are not going to buy. So that you don't waste your marketing expense and you actually market it to the people who are likely to buy. You are not going to be marketing, sending marketing material and wasting money to people who are not likely to buy. And let's say your company is selling some very expensive products. Now, which one is more important, which one is less important? If this is what your confusion matrix is. Okay, let me ask you step by step the questions. What is true positive yield? 3 or 2? Okay, so true positives 3 or 2. Okay, so you predicted they will buy and they actually buy. Okay, that's true positives 3 or 2. What is true negative? 725. You said these 725 people are not going to be buying, they don't buy. Correct prediction. Okay. False positive. How many for 175? False positive. How many for 158? Since the entire population has not been covered, how many 725? Okay, nobody. How many 302? Nobody. And this confusion matrix is more confusing than what appears. There is some hidden option also. Okay, 75 or 158. Okay, so those of you who said, I don't know, 158, why are you saying it's 158? False positive. You said 158. Yeah. Oh, it's okay. Change party. Okay. Good. So, because I cheated. I put predicted here, actual there, and actually negatives, positives, everything is completely messed up. But still, if you remember, when I say false positive, I am saying falsely predicted as positive. So, first I look at the predicted as positive. Predicted as positive, okay, this. And either this is false or this is false. Which one is false? Where the actual is opposite of what my prediction is. So actually here is negative. So this is false positive. This is false negative is falsely predicted as negative. So okay, what have I predicted negative? Okay, these are my predicted negatives. Which ones? Okay, this is anyway true because actual is also negative, so this is false. So false negative. Good? Okay. So false positive 75, false negative 158. Okay. Which one should the business be more worried about? False positives or false negatives? False negative. Okay. Why false negative? Okay. Okay. So chocolates. False negative. You as a data scientist, you predicted that they are not going to buy. You put them in this bucket, but they would have bought. You lost that business. Now they don't even know you are selling something like this. They are not going to come and buy at your place. Someone else is advertising. Maybe they will go buy there. Okay. False positive on the other hand. What happens is you said these people are going to buy. So you send your marketing catalog or phone call or emails or SMS, whatever you did, but they did not come and buy. You lost that money, that little bit money for your marketing. But that's not a major loss. That's why I said expensive product. Losing even one customer who would have actually bought, you are losing business. So in that sense, now, which one is going to be more important, recall or precision? How many recalls? How many precisions? Total of 4 or 5 people. Okay, so recall. What was recall? Okay, what is recall? True positive out of actual positives. Of all the actual positives, how many was I able to correctly predict? So, who are the actual positives? True positives and false negatives. They are actual positives, no? Actual positives. False negatives. And I should not be losing them. That's what I said. So recall is most important. I should be able to recall every customer who is going to be buying. Among all the people, precision, what is precision? Among all the people I predict, to buy, most of them should buy, but I may miss some actual buyers. In precision only tells the power of your prediction in terms of all your predicted positive, how many really are positive. Only out of predicted positive, not the actual positives. Recall of all the actual positives, of all the actual buyers, how many were you able to really recall? So, recall is far more important. You should be able to recall as many buyers as possible. Okay? Or the other another way I also seen. First, identify which one is more important. You said false negatives were more important. I say they will not buy, but they would have bought. So I lose business. False negative. False negative, which is it part of recall or is it part of precision? Recall is true positives divided by actual positives. So this is part of recall. Precision, true positives out of predicted positives. So this out of that is my precision. So this thing is coming in as part of precision. This is coming in as part of recall. So recall is more important. Okay. Great. So recall is more important. We have answered that. Okay. And all the other metrics. Okay. Confusion matrix, you have to practice. There is no way it will stick without solving the few problems. Okay. And where does it play a role? This is again my medical report from last year. Sensitivity, specificity. So this was anti-CCP, which is detecting rheumatoid arthritis. My value came at 0.48. Negative is less than 0.8, equivocal 0.8 to 1.2, positive 1.2. Is it a good thing or a bad thing? I came negative. Negative is good. You see, everything is messed up here. Negative is good because less than 0.8 is negative and 0.48. So there is no indication that I am testing positive for rheumatoid arthritis. But then, unfortunately, I know there is a bit more statistics than that. I read the whole thing. Normally, I would, if I did not know statistics, I would just read that and I will stop. And I will be happy. Now, I read this. It says, sensitivity of the method is 68% and specificity is 92%. And then I got worried a bit. What does that mean? Sensitivity, specificity. Sensitivity is recall, true positive rate. Specificity is true negative rate. So I said, okay, let me do some research. In India, rheumatoid arthritis is prevalent among 0.75% of adults. Google told me it. Okay, so I went and searched that. So then I said, okay, let me take a case of about 4,000 people. If there are total 4,000 people, 0.75% of the adult population has rheumatoid arthritis, which means about 30 people have it. 30 divided by 4,000 is 0.75%. Okay. And so then I put some numbers here. Now tell me, what is the sensitivity here? Sensitivity is the same as recall. What is sensitivity calculated? 20 divided by 30. So 20 anyway will be the numerator for recall, precision also, but we are not asking precision. So 20 divided by 20, actual, true positive divided by actual positive. Okay. And what is specificity? 3652 divided by 3970. True negative out of actual negatives. This is actual. Just first read what is actual, what is predicted. So this is actual negative. That is specificity. Okay. Okay. So I calculated that. Oh well. 68%, 92%. 68, 792. So, okay. So something similar to that is the result. Now it said I was negative. Well, I could be true negative, but I could be false negative also. There is that much probability of me to be false negative. I could be one of those 10 people out of 4,000 people. I could be one of those 10 people. Then I said, okay, what do I do? If I'm too worried anyway, then I'll get it tested again. Then your Bayes theorem will come into play. Naive Bayes theorem, not just the Bayes solve the problem. Okay. But that's what it is. This is all around us, the sensitivity, specificity that you are talking about. You will see them placed everywhere. Okay, not some theory stuff. So all that flashback now over. Let's get started with today's story. Any questions on the flashback? The most important things we learned were the confusion matrix and all these metrics. Of course, mean and standard deviation. Don't forget, because the rest of statistics that we will talk about is only mean and standard deviation. Okay, in various forms. Okay, so let's now start looking at, we covered probabilities, we covered statistics, we covered everything. Now let's talk about distributions. Statistical distributions, probability distributions. Okay, so for that, first definition we have to remember is of a random variable. Random variable is nothing but a variable that can take multiple values. Each value has a corresponding probability. Last week or 2 weeks back I mentioned simple example of a coin toss. What are the possible values the coin toss can take? Heads or tails? 2 values are possible. What is the probability of heads? 0.5. So heads, so it can take different values. Each value has an associated probability of happening. A roll of a die. 6 values are possible. What are the possible values for this random variable? The random variable is the roll of a die. What are the possible values? 1, 2, 3, 4, 5, 6. What is the probability of getting 1? 1 by 6. Probability of getting 2? 1 by 6. In these 2 cases, the probabilities are exactly the same. But for various types of distributions, the probabilities change depending on the situation, which we will cover. But that's what random variable means. It can take multiple values, each value has a corresponding probability. So here it is. Heads and tails. So discrete, so just like the variables, the probability distributions are also 2 types. Discrete probability distributions, continuous probability distributions. And we have seen it's countable, measurable. Okay. Number of runs Virat Kohli will score in the next test match. Discrete. Unless he is run out and you count that part of the run that so where exactly in the pitch is he here? Measure. So that, but if you don't do that, it's either 1 run, 0, 500, whatever, 200. Let's count. The time taken before Virat Kohli hits the next century. Continues. It could be next day or next week or whatever. 1.5 days, everything. Okay, good. So let's talk about probability distributions. First couple of rules. We have already seen some of this. The probabilities, the sum of all the probabilities is equal to 1. Okay, so this is discrete. This is continuous. The mathematical function that describes this probability, this shape here or this shape here, that's what the mathematical function is. That is called, for discrete distributions, it's called a probability mass function, PMF, or probability density function for a continuous thing. We'll talk about that. Okay, but either way, the sum of all the probabilities is equal to 1. This, the probability of this plus probability of this, 0.5 plus 0.5 equal to 1. Or probability of all the data, area under the curve. The moment we get into continuity, we get into integrations, integrals and all those things. We will not do mathematically, but it's the area under the curve. The total area is 100%. 100%. Heads, probability of heads plus probability of tails. Total is 1. Likewise, the total area under the curve is 1. Okay, and that's what I am depicting here. From minus infinity to plus infinity, the area under the curve is 1. Summation is 1. Total probability is 1. Doesn't change. Probability is non-negative. Whether it's discrete or continuous, it's non-negative. Now, the way we depict that is probability that a random variable x can take a specific value of x is equal to probability that the random variable x takes a specific value of x is given as probability of x. So probability that the random variable coin toss will take the value of x is equal to 0.5. Probability that here there is at a specific value of the variable. In a continuous, the probability at a specific value has no meaning. It's always zero. Specific value, area under the curve at a specific value here. And one particular area under the curve between 2 points I can get. This will be the area. But area under the curve under a line, that will be zero. I'll explain that a bit more. But that's what it's depicted as. The probability that the random variables between 2 points A and B is given as the area under the curve between points A and B. Let me take the example of heights of the people. Simplest example comes to my mind all the time, the same example comes to my mind. What is the probability that the, let's say, average height of people here is 5 feet 7 inches? Or what is the probability that, let's not even go to averages, we'll talk about samples later on, but what is the probability that the height of a person in this group is 5 feet 7 inches? Probability is how do we calculate? We calculate using the a posteriori frequent test. I count how many are there divided by total number. What do you think is the probability? I would say zero. Because when I say 5 feet 7 inches, in a continuous distribution, 5 feet 7 inches better mean 5 feet 7 inches. It cannot be 5 feet 7.0001 inches. It cannot be 5 feet 6.9999999 inches. It better be 5 feet 7 inches. That's what in a continuous thing. No, continuous, I said every value is possible. So 5 feet 7 inches, what's the probability? And when we say 5 feet 7 inches, we are rounding off everything. Everything more than 5 feet 6.5 inches up to 5 feet 7.5 inches. I am saying 5 feet 7 inches. Now that I can get 5 feet 6.5 inches to 5 feet 7.5 inches. That range may be very small, but I can get the area under the curve. But 5 feet 7 inches, what is the area under the curve? Area under a line is zero. From 5 feet 7 inches to 5 feet 7 inches. If you calculate area, it will be zero. The probability of having one specific value in a continuous distribution is zero. Because it only depends on how you are rounding off. Rounding off is a different thing, that's for convenience. But when I take the specific value, it's not possible. Okay? Maybe 1 in a million, might exactly, with the finest scale that I can have, if I do, maybe 1 in a million will have exactly 5 feet 7 inches or 2 in a million. It's almost zero, equal to zero. Close to zero. So that's what, that's why in a continuous distribution, if I ever ask you what is the probability at a specific value, the answer is going to be zero. The range can be very, very narrow. It can be infinitely narrow. Where you can calculate the probability, but it cannot be one value. Exact one value. Okay? So that's what, this is the probability density function, this is the probability mass function. Okay? But like I said, if we talk about these things like this, then that's where the statistics gets boring. Okay? How many of you know histograms? One. How many? 2, 3, 4, 5, 6. Okay. How many of you know bar charts? You all know your probability mass function and density function. There is nothing new I can teach you if you know your bar chart. Okay? Let me just say how that is the same thing as a bar chart. Minor variation. continuous thing. And if there is a gap, that gap means that there is no data there. Okay. So first let's talk about the histogram. I will show the histogram with some data. And the x-axis is some pins. The histogram, the entire data is broken down into some pins. Now, age, for example. I may ask everyone's age here, and someone will say 16 years. Many will say 16 years. Ladies especially will say 16 years. Okay. Well, I am about 25, so that's okay. So we will all give some range. Okay, and the age range is from 16 years to, let's say, 35 years. Let's say 50 years. Okay, so that I will also be part of the group. Let's say 47 years to be specific, to be precise. Not just 47 years. 47 years and a few days. Okay, let's forget it. 16 years to 47 years. That's the range. That's the x-axis, age. I want to now, if I say probably one person from every age might show up. Bar chart. Here, 16 years, one person, 17 years, two people, 18 years, five people, like that. But instead of that, I might want a group. I have too many groups there. So I will say, let's say 16 to 47 is my range. Maximum minus minimum. And so what, about 31 years? Let's say 46 years. Okay, 16 to 46, 30. 30 is the total range. Let me break it down into some intervals, 5 to 15, rule of thumb. So let's say 5 intervals. Or 6 intervals. 6 intervals, which means 30 range is divided into 6 intervals. Each interval 5 years. So what I will say is 16 to 21, one group. 21 to 26, 26 to 31, 31 to 36, 36 to 41, 41 to 46. These are my pins. I have pinned the data. And now I am counting how many are between 16 to 21. And my y-axis becomes the frequency. Now 7 people are there. Okay, 7. 21 to 26, 15 people are there. That's what histogram. And now there is no gap in the x-axis. You see, 16 to 21, 21 to 26. It's all continuous. If I draw a histogram and show the gap there, that means 21 to 26 nobody was there. The gap has a specific meaning in histogram. Other than that, it's a bar chart. So, and the rule of thumb, 5 to 15 pins is good enough. If you are mathematically inclined and you want to trouble yourself more, learn about that Friedman dichotomous rule, where again you are only using range and interquartile range and all those things. But if you care about it, I don't. I will just make it in 7 pins. Okay. So let's do that with a couple of data sets. I'll share the data sets. The screenshots are here. So I have the annual traffic data for 30 busiest airports in the world for 2 different years, 2013 data and 2011 data. Atlanta had 92 million passengers in 2011, 94 million in 2013, like that. The last one was Istanbul with 37 million and Munich with 38 million here. That's what it is. So, what is my range? From 37 million to 92 million or 38 million to 94 million. So I'll say, okay, 30 million to 100 million is my overall range of these top 30 busiest airports. Let me create a histogram. Let me create some pins, 30 to 40, 40 to 50, 50 to 60. Like that I will do. This is what I did. 6 of the 30 airports had more than 30 million and less than 40 million. Then 11 had more than 40, less than 50. Like that. There is a gap there. That gap means there was no airport on the top 30 airports which had a traffic of more than 80 million passengers and less than 90 million passengers. That's what it means. So this is histogram. This is exactly a histogram. Histogram is a plot of the whatever. Okay? So anything. Incomes, anything. How many from this range to this range? This is just broken down into bits. So y-axis is always frequency in histogram. Keep in mind two things. One, the shape of this data depends on the bin width. Suppose I had taken 30 to 50, 50 to 70, 70 to 90, then this would suddenly become 30 to 50 would be 17, and then 50 to 70 would be 6 and 5, 11. So here, and then 70 to 90, just same here, 9. So suddenly this would become show up like this. So it depends on the bin width. So histograms are very popular ways of understanding data. You will be plotting them regularly all the time, just like your box plots. But keep in mind, don't make final decisions based on the look of the histogram, because it depends on the bin width. If you want, change the bin width a few bits, different bits, and see how the shape looks. If it continues to look the same, then you have some understanding of that. But it's a good one. 2013, see how it changed? Changed from here 30 to 40, 40 to 50. So here 40 to 50 there was 11, and 50 to 66 they became 8 and 9. Actually something similar was just going on. They moved on basically, and there was an airport with more than 80 after 90. The other thing is, these are plots, part of communication. Make the communication very clear. If you use the software, it might automatically just put 30, 40, 50, 60, 70, 80, 90, 100. If you understand that, it's fine. But I don't understand it. Because if I say 40, if there was an airport exactly at 40 million, would that be part of this group or this group? It can change, or it can suddenly make this one go up or this go down, or something like that can happen. Or if there are many values at 40 million exactly. The rule of thumb again is to actually use that in the next one. So if there is 40 million, it goes to the next thing. That's why I have written 30 to under 40. And that's very important when you are doing communication. Please, it doesn't matter what the software is outputting. You make your communication very clear. You use a text box in the Word document or something and put it on top of what the software has automatically printed. Hide that thing. Crop that off. It doesn't matter. Communication is important. So 30 to less than 40, whatever you might want to say. Or you can say 30, 40, 50, 60, 70 and put a legend under that or a statement that the values at the intersections are actually in the following bin kind. Just trying to explain the importance of communicating it right. Okay, but histogram clear? Histogram clear. Okay. Now that histogram is clear, I will show you how you already know your all the probability, mass function, and density functions. Let's take an example of some analog signal from an 8-bit analog to digital converter attached to a computer. 0 to 255 millivolts is the signal that you are getting, and when you are digitizing it, it is converting between numbers from 0 to 255. Okay. The analog signal itself